Okay, welcome back Physics 20s to our next lesson in Chapter 5. This is 5.2, and today we're going to be looking at some centripetal forces. Alright, so anytime something is going in a circular path or even just a curve, we're going to call that circular motion. And this can apply to a whole bunch of different scenarios. This could apply to a car driving around in a curve, a satellite going around Earth, or even a simple example like this, where if these keys swinging around in a circle. Now, if we have an example like this, the key swinging around in a circle, this is technically called accelerated motion, even if it's going at one speed. The reason why it's called accelerated motion is the direction is changing. And since velocity includes direction, if our direction's changing, our velocity's changing, so therefore it's accelerated motion. We focused on that a little bit more in the last lesson. Today we're going to focus on the other part of acceleration, which it has to be caused by a force. So anytime something's going in a circle, there has to be a force that's putting it into a circle. So let's take a look at a diagram here of those keys going around in a circle and see how we can talk about the forces. The first way I'd probably actually look at it is, what if there were no forces? So if we're swinging around here and we let go of the keys are going to fly upwards at a constant velocity. That's Newton's first law for how an object's going to act when the net force is zero. It's going to go in a straight line at a constant velocity. So what's going to prevent the keys from doing that is we're going to apply a force. So to stop it from going off in that direction, we have to pull it back towards the center of the circle. So this little spin here will show the direction that the keys are traveling and would continue traveling as they go in a circle unless we pull towards the center of the circle. Okay, so right here it would fly off in that direction, but we pull it back. Here it would travel down, but we pull it back. There always needs to be a force to the middle, and we're going to call that required force to go in a circle the centripetal force. Okay, now the centripetal force doesn't come out of nowhere. Things just don't travel in circles on their own. A force needs to be applied to make it go in a circle. So something needs to provide the centripetal force, and in this example, it would be the force of tension. So whenever something's going in a circle, we say Fc is present, look for what's causing it. In this case, it would be Ft. To start solving with equations, we say Fc is equal to the force of tension. Okay, so Fc equal to whatever is providing it. And we saw from last lesson our equation for Fc is mv squared over r. So here if we wanted to solve for tension, or if we had tension and want to solve for any other variables, we'd be able to do that from this equation. So let's just put some of those key ideas into the notes here. So first off, reminder that circular motion is accelerated motion. Now looking at the force part, for circular motion to occur, there must be a net force or an overall force towards the center of the circle. We'll see in the next lesson with vertical ones, there can be multiple forces, but overall there needs to be a net force towards the center of the circle, so it keeps traveling in a circle. Okay, this has to be provided by something. Again, it doesn't come out of nowhere. It could be provided by tension, normal force, or friction. Those are the three we're going to look at in this video, or it could come from others, but we're going to focus on those three. So before we leave tension, let's do an example where you had to solve for some values with swinging something around on a circle. So we have a 150 gram mass. It's swung in a horizontal circle on an 85 centimeter string, and there's a 10 Newton force of tension in the rope. What's the speed of the mass? Okay, so how to start these questions? Whenever we know that something's going in a circle, we're going to start with Fc equals something. In this case, the Fc is provided by tension. Fc is equal to Ft. Okay, the formula for Fc is so is mv squared over r. No formula for Ft, that's just the value of tension. This one's a little bit different. We're trying to solve for the speed, so we're trying to solve for the velocity in this equation. So we'll times by r, divide by m, and take the square root to rearrange for v. And now that we have our variables all set up, we'll plug them in. 10 newtons, 0.85 meters. So as it's spinning around the length of this string, it's going to make a circle like that. So from the center of the circle to where the keys are, that is the radius of the circle. It's the length of the string. So that goes into 0.85 meters, and we have to put the mass in as kilograms. So 0.15 kilograms, get our answer as 7.5 meters per second. So a pretty high velocity. Next, we have a very similar scenario, but we're going to change it just slightly, and that now we have a marble going around in a circle and no string. So maybe this is like on a desk, and we have a wooden circle, and I'm going to push the marble upwards so it's going to start rolling. it's going to hit the edge of that wooden circle and start spinning around. So when it's going in a circle, we know it's going in circular motion. There must be a centripetal force. Okay? But in the last example, there was tension pulling it to the middle. We don't have tension in this case. So what could be providing that centripetal force? Well, it seems like it's coming from that kind of wall or wooden disc. What would we call that force? Well, it's kind of like a surface pushing against the marble at 90 degrees to the surface. Hopefully you remember from chapter 3, that pressure in between surfaces would be called the normal force. The rest of the calculation would be identical to the last example we had. We say Fc because it's going in a circle equals whatever is pushing into that circle, and then put an mv squared over r for Fc. In this case, there's no equation for Fn because it's just the sideways force pushing on the marble, so we don't calculate it by gravity in this case. It's just how much pressure there's between the marble and the wall there. Okay, so we want to solve for that pressure. We'd have to solve it using mv squared over r. And just to be clear, if this was on a desk, we're not talking about the normal force opposing gravity, like pushing gravity onto the desk, normal force of the desk pushing up. This is just looking at the side-to-side force, the side of that kind of wall of the wooden disc pushing in on the marble. In case it's still not quite clear what that would actually feel like, imagine you were on a roller coaster and it makes a turn and you feel like you're pushed into your seat. That's kind of the normal force that this marble is going to be experiencing. It's not the same as gravity, it's the pressure between those two surfaces. So imagine like you're taking a curve on a roller coaster, being sucked into the seat. That's kind of the force we're calculating here. Okay, the last example we're going to look at is probably the most complicated, and it's where we have a car or a bike or some sort of vehicle like that going in a curve. And it's complicated because it is going in a curve, so we know there has to be a centripetal force towards the center of the circle, but there's no wall ride here to push it to the middle, and there's no string pulling the car into the middle. So what's the forces pushing it to the center? Actually turns out to be the frictional force, the friction between the tires and the road. Maybe to see why it is the frictional force might help to see what if we got rid of friction, kind of like when we let go of the string earlier. If there was zero frictions, like super icy, the driver's going to be driving forwards, turn their tires, but without any grip, they're going to go in a straight line. Again, Newton's first law of inertia says we're going to go at a constant velocity in a straight line if there's no forces. So we need that grip to pull us in towards the center. And this is kind of how I imagine the force. There's a couple ways to do this diagram, but I think this one makes some sense. If we take those tires and we turn them towards the inside of the circle, imagine like it was going to try slipping and moving forwards. That would apply a force pushing the asphalt this way. That grip is pushing the asphalt in this direction. Okay? And kind of similar to an inclined plane, if it's on an angle, it's going to push perpendicular to the surface. So we're going to get a force pushing on the asphalt like this, and due to Newton's third law, the asphalt will push with an equal and opposite force on the car in this direction. And that arrow matches this picture, showing that it's towards the inside of the circle. Okay, so if we're doing calculations here, Fc, because it's going in a circle, is equal to Ff. Fc is equal to Ff. In this case, we know Fc is mv squared over r, but it's a little more complicated for this one because Ff has an equation. Normal force times coefficient of friction. Now again, this isn't the normal force of like pushing against a wall like the marble was. This is the normal force against the ground times by the coefficient of friction. This came from the earlier friction lesson. If you need a review on that, you can go back and watch that one. So that's saying the grip between gravity pushing down on the car and the asphalt pushing up on the car, the pressure between those surfaces is the normal force. Okay, that times the coefficient gives us our grip on the road. So how can we calculate that normal force? Well, if gravity is pulling down with a number like 1,000 newtons down, to stop the car from falling through the road has to push up with 1,000 newtons, and it's staying flat on the road. So as long as it's a flat road, which all our questions will be, it's going to have an equal to the gravitational force is what the normal force is. So how to calculate Fn, let's throw in mg. Okay, so mg gives us force of gravity, which is the same as the normal force on a flat road. So now our equation is mv squared over r equals mg times coefficient of friction. Okay. Why this is so interesting and useful is that it actually doesn't matter what the mass going around a circle is, because we have a mass on one side, mass on the other side, so we can cancel them in this equation because it's in every term. What makes that so interesting is that if we're trying to calculate how fast a vehicle could take a curve without slipping, this equation does not involve mass. Meaning if you had a light car or a heavy truck, it's not going to be a factor in how fast we can take this curve without slipping. So what is going to be a factor? Well, we're going to have to get rid of this equation and let's just rearrange it without the masses for radius. So let's get rid of that, rearrange for r. The reason that we're rearranging for r is going to tell us how tight of curve we can make. If we can get a small r value, you can drive a tight curve with control. But if you get a big r, the only radius of curve that you can take is a large one. You can't make a small curve. Okay, like this diagram shows, a small r, we can make the corner. If my r becomes too big, then we go, unfortunately, into the ditch. So let's see what is going to affect our r value. Things that are going to affect our r value: if the coefficient of friction goes down, dividing by a lower number, our radius goes up. We can only make big turns or else we'll slip. The other thing that affects that is the velocity. If we're going faster, we can't travel as tight a curve without slipping. Okay, so how can we control this? If it does get icy, what are the two things we can do? First one is we slow down, decrease that velocity, so that when v goes down, we can drive in a tighter curve, and that's probably the biggest one. The other thing we can do, we can't really change the ice on the road, but we can change the coefficient of friction with the tires. So if we put on winter tires, which are important for when we have icy conditions, or ice tires if you can, then we're going to also decrease that radius, make it so you can drive a tighter curve without slipping. So these are the laws of physics. We can't really beat them. These are the only two things that we can control. And we'll assume g is the same. We're going to imagine we're still driving on Earth. So to further this point, let's do a calculation with some actual numbers. What's the maximum speed a car can take a curve of 100-meter radius in the summer when the coefficient of friction is 0.8? So dry roads, good asphalt, good tires, 0.8 coefficient of friction. So how we start all the questions from today's lesson is FC, we're going around a curve, equals something. In this case, what's making it go around on a curve is the friction. I see it says T there. It's supposed to say F, the force of friction. So imagine that's an F. Then we plug in the equation. This part is correct. mv squared over r equals mg mu. That is the force of friction, mg mu, or mg coefficient. Again, we can cancel out m, rearrange for v, and we get v is the square root of gur, g, gravity, coefficient of friction, and radius. I can always remember that. Square root of gur tells you the velocity it goes at. But we plug into those numbers, 9.81 for gravity, 0.8 for the coefficient, and 100 meters for the radius. We get an answer of 28 meters per second, which is the same as 101 kilometers per hour. Now admit, this is a pretty tight turn, so you can go all the way up to 100 kilometers per hour on dry roads before you start to skid a little bit. But I mostly want to make this calculation to compare to what if it gets icy and the coefficient of friction drops to 0.15, which is a realistic coefficient of friction for icy conditions. So we do the exact same calculation. Again, Fc equals to FF, imagine that's FF, not FT, equals mgu. This part is correct. Canceling out is correct. And we get the same correct equation of a velocity is a square root of gur. Plug in, and now we use 0.15, and we get an answer of 12 meters per second, or 44 kilometers per hour. So this is what I think is important. Before it was 101 kilometers per hour, and now we're down to 44 kilometers per hour. So sometimes when people think, I just have to slow down a little bit when it's icy, there's a significant change in the velocity that your car can go before slipping. And that's when the slips often happen, is on a curve. We try and curve and end up going in the ditch, or we had to curve to correct and try and go straight, and again, that didn't work out and people get in accidents. So kind of proof here that we need to reduce the velocity and increase the coefficient as much as we can with tires. And just to conclude here, we looked at 3 different scenarios today. All of them, if they were left on their own and no force was applied, they would continue off in a straight line due to Newton's first law. So we have to apply a force towards the center of the circle and provide the centripetal force to make it go in a circle. All of them towards the center of the circle. We're going to say Fc is equal to something. In the first case, it was due to tension, and our formula for Fc was mv squared over r. Pretty much the exact same case for the second one. It just wasn't tension, it was normal force between that surface. The last one was the trickiest. Fc was equal to force of friction, and we put the force of friction as mg mu, and again, the masses cancel. Hopefully those equations help you to answer all the practice questions. Thank you so much for watching this video, and I will see you in the next lesson.